Welcome back to the workshop. So in this video series we're trying to build a spindle load monitor to stop this kind of thing happening. In the previous video we got all the way to proof of concept, so it does monitor the spindle and when it stalls it triggers an e-stop. So in this video we'll develop the concept a little bit further. So the last video I used this Arduino Uno to do all the processing. Now it did actually work, but I had very little code running on it, and I was worried that as I had all the functionality, user interface, things like that, I was perhaps going to run out of processing power on this. So I decided to upgrade to this. Okay, this is an ESP32. It's a much faster processor. It's got about 15 times the speed. It's got Bluetooth, Wi-Fi, lots of inputs and outputs. This particular one here is a 30-pin model, slightly smaller, but I thought that's perfect for my needs. And the other thing I've done is, this is my old board. It was getting a little bit small and difficult to wire up. So now I've got this. Okay, you probably recognise it already, but this is the Gridfinity system. So I printed out 3 of these, and then the only thing I did is added these little screw lugs on the side to mount it onto this wooden base. And then these are some trial parts. So there's the Gridfinity system, and then all I did is made sure the lower part had enough feature on to go into each of those. And then I've got some little modular units that I can add circuits in and out and configure the wiring and hopefully be a little bit easier. At the top here I've got the power rail, so this is the positive side, and then I've got all these little banana sockets in and plenty more spaces for more as I expand the system. And then down here we've got 2 possibilities. So if you're just running it like 0 volts to something, then you can just use this rail here. If you're using an op-amp that's got dual supply where you need to go plus and minus and then have some kind of 0 as well, then this could be the negative rail. So you'll have positive up there, negative like plus or minus 12 volts or something, and then 0 in the middle. So we've got that option as well. Okay, up here you've got the inputs. So we've got 2 sensors there which go in via jack plugs, and then we've got a barrel lead type if you want auxiliary power for something, and then space to add more over here. So here's the basic idea. This is a 2x2, but it could be any size really, and that's just a breadboard ready to go. So you've got power there, and you've got these little fish brackets or fish plates, whatever, that you can jump across. So you've got 3 inputs, 3 outputs, power, however you want to do it really, and then the space to get the wires above or below. At the moment I'm putting all the wiring, all the circuitry on the top, so it's easy to see, you know, what each one does. It doesn't look quite as neat, but it's easier to keep track of what you're doing there. And you can imagine things like this. That's an op-amp used as a comparator, which is not ideal, but it does work. You can see how kind of messy and intricate that is. Yes, you could use the little wires instead of these, but if you had it hard soldered onto there, you could have a kind of generic op-amp that you drop in for all sorts of applications, and then you kind of build the blocks up to make whatever circuit you want, and then because you've got the banana leads it's a little bit easier to do your signals and your power. So yeah, I like it so far. I think it's going to come in pretty handy. Okay, quick overview of what we got then. So on the inverter, the output for the speed is a PWM trace, and it's 0 to 10 volts, and I want to drop that down to 5 volts, so we've just got a basic voltage divider there. So I haven't got it hooked up yet, but the signal will just go in here and it will go from 0 to 10 to 0 to 5. And then this one down here is a low pass filter. So we've got 2 of those. The top one's coming from the IR sensor, just to filter that a little bit. And then the second one, is the one I've just got looped across from here. This is the PWM signal from the on the inverter. So if you put a PWM signal through a low pass filter like that, you just get an analog voltage out of here that's proportional to the speed. And as long as that's kind of sort of fast enough to keep up, you'll get kind of a real-time signal, 0 to 5 volts as an analog signal that relates to the speed, and then that goes into the ESP32. The other things that go into it, obviously we've got the output from the low-pass filter from the infrared sensor that comes from the spindle, and that goes into one of the pins, and then a load of the other ones come out here. I'm not using the I2C network on this one, it's more direct because it's got the keypad on. I don't think there's one way you can get all 3, but anyway, it means more wires, but that's okay. And then there's our screen there, and then the output that drives the relay comes out of here and into this blue one here. And at the moment I've only got space to put one on, so I can only use one of the relays like this, but I think that's okay for now. and then the e-stop will come into normally closed and the common on whichever relay I'm using. So that's a quick overview. Let's hook it up to the machine and make sure it works. Okay, I've got everything connected here, and I've got the sensor hooked up to the spindle, and we've also got our PWM output from the VFD inverter, so we can look at the speed that the inverter wants to run at, like the speed demand, and the actual speed of the spindle. And we've got both those shown on the display down here. Okay, there it is, all connected, system's on, and we've got the scope hooked up because we're going to show you one of the issues that I discovered in the last video. So you might remember I was having trouble with the pulses coming out of here using interrupts, and it was giving like 10, 20, 30 pulses every time one of the little white segments went round. It should have just given one. When we look closer at the signal, I think we can see why. Okay, we've got the scope set up, looking at the pulses coming back from the spindle. That's the infrared sensor. This is the one I had trouble with using interrupts. I'll just run it. So the pulses look okay, but if we zoom in, we have to go quite a long way, and we'll try and capture a single one. I think you can see they're a bit variable. Now that's a good or a bad one. So you can see there where each of these would be triggered as a change, so that would be counted as a pulse, and then it would come back up and then wavering about, so it's getting multiple triggers essentially. Something like that. So we need to do something about that and filter it out. So now I've got our low pass filter, that's the top one here, connected, and we've got the scope looking at the output of that, and now we've got that going into the ESP. So let's see what that looks like. Start the spindle. Zoom out. Okay, so you can see the effect of that filter. It gives a slight roll off, but in terms of counting pulses, that's fine, because we just need to know how many pulses we've got. And we're on a 0 to 5 volt scale there. If we zoom in, just capture one. Yeah, there's a very slow roll off, but slight roll off. But if we look at that in time, it is pretty small. So, it depends where you want to count it from, but it's like in microseconds. Okay, so that's the spindle output sorted out. Now we need to have a look at the VFD output. So we'll just switch the yellow one off for a minute, and we'll zoom in on that one. Now I'm zooming in quite a lot, but you can see it's quite noisy. Now that's already gone through the low pass. If we look at what it's like before, hold on. So that is here. So that is before the low pass filter. So let's just run it. It captures a single frame there, so I think that's before the low pass. Let's do after. What's that one? And we'll run it. So I've gone through the low pass, so it's smoothed it a bit, but if we zoom in, we've still got little jumps. Now that might be making it fluctuate, so we'll see if we can clean that up. We'll bring a comparator in, or at least an op amp, and see if we can make that in a little bit cleaner. Okay, I don't know if you noticed in that run up, it was reasonably okay, but there were a few little dropouts, which got some dropouts on the readings, and clearly that's not going to be good enough because it was making it go into e-stop, which is clearly not what we want. So, we want a really clean, reliable signal. So I've basically redone the circuits again. So we've still got our voltage divider to drop the 10 volts pulse down to 5 volts pulse. That's going into our op amp comparator to try and make that nice and clean, and that's working really well. So that's what's coming out the inverter, so that's those two. And then this one did have a low pass filter, or just a fixed value low pass filter, and so what I've done, I've still got it hooked up to that really tiny value capacitor as a low pass, but now we've got a variable resistor in there. And so what I've just been doing is playing around with the value of that until I get the roll off looking as sharp as possible, but still cleaning up the signal. So kind of find the sweet spot for that. And then after that I just did some various run-ups and just made sure that the signal was good all the way up to 24,000 RPM. So that's looking a lot nicer. Okay, during testing I've noticed some other little problems as well, particularly if you start and stop the spindle. It seemed to be tripping out the display and causing these strange characters to appear on it, and the only way to get out of it was to do a reset on the display, which was fine, but I wanted to try and avoid that. So I've tried a couple of things like putting a big capacitor across the power supply. I was checking the voltage, we get about 4.85 volts, and I put that on the scope and it was nice and steady, so we weren't getting like a brownout. So my only thoughts are maybe I was getting some interference from the VFD, because after all I'm taking those signals from the 10 volt PWM and bringing them out into the ESP32, which is connected to the display, so I wondered if it was related to that. Okay, so just to see if there's noise in the system from the VFD, I've separated it using this ISO coupler, and this is a module of 4, I'm just using one of those, and the PWM signal 10 volt comes in there. I've got a little current limiting resistor. We'll go into the data sheet in a minute and just explain the value I've gone for there. And then there's our ground, which completes the circuit. So this side is on the VFD side. Then inside each of those you've got a little LED, and it shines on a little optocoupler, which is like a kind of transistor, and when light shines on it, it passes current. It's like a switch, or you can use it in the linear region. I'm using it as a switch, so when the pulse comes in here, as long as that LED is bright enough, on a completely separate circuit, it should send the pulse out the other way, and then all this side should be completely isolated, or at least it can't get through that route there. That's the plan anyway. So I think the way you're supposed to use these, obviously you've got the inputs over here to trigger the LED, and then on this side you've got the outputs, and these go across the transistor. So one's to ground and one's the emitter at the bottom of the transistor. So it kind of joins those two together. The problem is you can't source any current from that, so you can't bring it up to 5 volts. So it's really just a kind of trigger if you want to trigger a load, I think, downstream on the ground side over here. I don't want to do that. I want to actually have pulses, and the problem is there's a little, let me just about see it just there, there's a 3k resistor which is on the output there, and I don't really want that. I want to go direct. So as you can see, I've soldered directly to the output, and then I can use that 3k resistor as a pull-up to the 5 volts, which is what we got here, and then this ground just goes to ground. And basically what happens then is that leg there, which I guess is pin 3, if it's off, then it will get pulled up via that little resistor to 5 volts, and then when it's on, it will connect it to ground and we'll go from 0 to 0. If you don't do that, and you try and come out the output here instead, you just get some small value. You'd have to put some, I don't know, some other components in there. So to cheat, I've just gone direct off the pin. If I use this in a final circuit, then I'll just buy some of these and make my own custom board. Anyway, that's what we got. So we should have pulses coming in, and let's have a look at the pulses coming out. So we're looking at the output of the optocoupler. This is on the other side now, on this side of the circuit, and that's 0 to 5 volts. You can see it's about 4.8, which is what I'm supplying the rails with, because I'm running off the USB off the PC. So when this is finally done and it's not plugged into the PC, it's running independent, it'll run off a proper 5 volts. So anyway, for now that's where we're at, and you'll notice it's high because obviously it's being pulled up, and then the pulses are low, which means I've got to change the code round, so the duty cycle is counting the lows as pulses, not the highs, but we'll get into that in a minute. Right, let's just start the spindle, and you get a nice clean pulse. Okay, even if we zoom in on it, it's a pretty clear transition. Just jump around a little bit, which is a bit worrying, which will probably mean it'll vary the RPM slightly, but in general looks pretty good. Obviously you get wider pulses as you go faster. I haven't tried, does it go all the way to 24,000? Let's have a look. It might not be fast enough. Oh yeah. Now the idea of the optocoupler was to try and separate the VFD side of the circuit from this side, at least going through this route. Problem is, I just ran it up and stopped it. Yeah, you can see there's some random characters appearing already. And the only way to get rid of that is to press the reset and pull this pin up, put a wire between here and 5 volts. So, not ideal, so there must be another reason why the display's no good. Now, the other thing I've done, I spent a few hours making this custom board. You can see that it's on, and I've got proper pins and headers. That's nice and tight, so the cables are really good into there, whereas before they were on those little, you know, those sort of little square push connectors. So I'm pretty confident that the wiring's good and solid and there's no issue there. There's obviously something else going wrong. Speaking of things going wrong, last night the PC, when I booted it up, started doing this. So it's not switching on, as you can see. Doesn't even get past the post test, and the fans are on full speed. And it won't start up. Well, I've just taken it outside and blown it completely out with an airline. There was a lot of dust in there, as you can imagine, but I'm not sure it's overheating because it's literally when it's switching on from cold. Now, the last PC that did this ended up being the power supply, but yeah, it's pretty old. Maybe it's that again. But what we'll do now, we'll just reseat the memory and the graphics card and just might get lucky, but I suspect it's the power supply. Anyway, let's do that and then we can try it again. Right, I'm just taking the main power connector, it's a 6-way, off the motherboard there. I'll just see what we've got. Uh, 11.3 on that one, 11.3 there. And then the other cable coming from the power supply is this one, and I'm just taking it off, and we've got 4.2 between those two. Just trying another boot up just in case. And the green light. Yeah, when I took off the little auxiliary connector there, it wasn't fully home. I wasn't far away, but it was just slightly off, and I just wonder if it wasn't making a good connection. That's possibly working. Here we go. It's working, back in business. So I've rewritten the code so that it turns the pulses the other way, so it counts the lows as highs. We've got our scope there monitoring the two signals, one from the infrared sensor on the spindle, one from the inverter, and we're using our opto isolator for the inverter. Okay, so about 3,500 RPM. Opto coupler's on. Let's increase the speed. It's looking pretty good. Now let's stop it. It's gone again, even with the opto couplers, so must be something else. Okay, we've got a new setup, so I'm no longer powering it from the computer via the USB. Instead, I've got this independent 5-volt power supply, and then that in turn is plugged into a really long extension cable that's plugged in on the other side of the workshop. So we should have a fair bit of isolation between the ESP32 and the inverter. So let's stop it, start it, run it up and down, and see what happens to the display. Start it up. Decelerate. Accelerated too much. I'll have to tune the parameters. Anyway, carrying on for now. Let's stop it. Okay, still good. Normally that would trip it out. Okay, eased up again, but that's okay. Yeah, looking good. So I was just doing a little bit of reading about those LCD displays. That's 16 by 4. I'm running it in 4 wire mode rather than 8, just to save on pinouts on there. Now if you do that, then in the library it has to send nibbles, which is half a byte. So a byte is 8 bits, nibble is 4, so it sends 4, then the other 4, and then it's next byte 4 and 4. It's critical that it stays in sync, otherwise you get this garbage message, and once it goes out of sync, that's it, you've lost it. You have to do a reset, or you could use the begin command to start it again. So one option would be, every 5 seconds or 10 seconds just reinitiate the display, just in case it is corrupt, or every time it comes to idle, because you've probably stopped it, reset it that way. But yeah, it feels like a workaround, and this looks like it's working so far. So running off the independent power supply, that seems to have done the trick. So obviously something from the inverter when you stop or start was going back into the PC, because they are plugged in next to each other, and then somehow that was going through the power supply and into the ESP32 and onto the display. Okay, so a quick look at the optocoupler then. So out of the inverter I've got V0, which is putting out the PWM pulse between 0 and 10 volts, and it's a duty cycle, so the longer that pulse in that given time window, the faster the motor's going. Now it did say in the manual there was a limit of 10 milliamps, so we need to be careful of that. And then to take care of that, then I added this current limiting resistor here called RD. I'll have a look at that in the spec sheet in a minute. And then inside the inverter, it goes through the infrared LED here, that's obviously then going to flash on and off in time with these pulses. And then inside here is an indicator, so you can see what's going on. They've got a 1K resistor and a green LED, just so externally you can see that it's actually working. And then that goes back to the analog common ground here. So this is our signal, and then that's the ground. So that side is all completely isolated from the signal that we want on this side. So then when there's pulses flash from the LED there, they fall onto this photo transistor down here. And then, so when that's off, well, let me just show you how they've got it configured and how I'm using it, which is slightly different. So ignore that out for a minute. Normally when that's off, they have it connected to this 3K resistor, which goes to the output. So you could hook that up to be some kind of on-off, something's activated. But I want this to be like a buffer amp or a unity gain. I actually want it to follow the pulses between 0 to 5 volts. So I've done something a little bit different. So rather than, so technically the output is actually there, I think they call it V1, off that resistor, and it looks like that. But that doesn't really work for my application. Obviously I want these pulses, so I'm not using that. And essentially I've pulled that up to 5 volts, and then you'll see I've soldered on a little cable off pin 3 of the optocoupler, and then that is my output. So obviously when I do this for real, I've actually got some of these chips on order. I can configure this how I want. Anyway, so if you pull it up to 5 volts like that, when the transistor is off, you obviously get 5 volts like that, and when it switches on, it pulls this point down to ground. So this is our pull-up resistor, and the one on board is 3K, and we'll have a look at what that means in a minute in terms of response time, upper frequency and things like that. But this layout works, and you actually get these pulses that go down to 0 when this goes up here. And note that this is now 0 to 5 because my pull-up was 5 volts, and then that's quite happy going into the ESP, so we've got a nice signal. Okay, so in terms of specing some of these components, I've drawn, so that's kind of right, but obviously I'm now pulling that V1 up to 5, and then I'm having my output come off here, so I get my 0 to 5 that way. Yeah, so that's how I've done it. Right, so in terms of the inverter, it has 10 volts coming out. It said 10 milliamps, I guess, is the maximum, so we've got to be a little bit careful. So that's RD. So in that circuit there, I just ran a few values, and 1K gave me 10 milliamps. Now actually I was having a look at it, I didn't realise, I think they've got that LED and that resistor in series with the output, so actually I'm probably a lower current than that. I'm probably nearer double that, but that's okay, it does seem to work. So we're certainly triggering, and I guess because it's working, we're saturating the transistor, or photo transistor on the other side, so I'm going to leave it. We're definitely under 10 milliamps, so hopefully the inverter's okay and it's working. Right, so that's the input side sorted out. We've got an appropriate resistor, so as you can see, they've actually got their indicator LED in series with that So we're pulling less than 10 milliamps, but no matter, it works. Right, now onto the output side. So I've already said I've added that pull up to 5 volts, and then I'm ignoring V1, and then my output, which I've soldered on that cable, comes out here. So in terms of tuning that resistor there, that 3K, we've got some options down here. So here obviously we're running 5 volts now, and I've just varied the resistance and looking at the current that comes out of there, and noting that the maximum across the transistor is 50, so we're well within that range. Okay, so the standard onboard resistor is 3 kilo ohms, 3000 ohms there, and if you look at that in terms of, we've got it here, it's in one of the other data sheets, but so let's just get that. Hold on. Actually, it's under here, isn't it? Okay. There's quite a lot of data sheets for this. So in terms of the response time, that's down here. So we've got frequency, and I've interpolated a little bit. It's a log scale, but 1K, so 3K is probably going to be broadly there, and our 0 point, which is where I ideally want to be, I don't want to be rolling off, is about 4 kilohertz, which is the spec they give you. They say don't use this above 4 kilohertz. So that all tallies. So can we change that value if we wanted to make it a little bit better? Yes, we can, but one of the reasons, or why might we want to do that, one of the reasons is the response time. So it's not infinitely fast. So as it receives a pulse, there's a small amount of time before it decides it's going to do anything, and then there's a small amount of time that it takes to actually change states, and then the same the other side as well. And these sides are not totally symmetrical, so the switch on and switch off time are not the same. And essentially what happens is, as you reduce this value, you can switch it on faster and switch it off faster, so quicker response, go up to a higher frequency. The trade-off is, as you make that lower, you're pulling more current, so you're going to pull more current on that transistor. Yeah. How far do we need to go? Well, I was prepared to play around with this. This is why I made the spreadsheet, to tune the RL value to make sure it's going to be fast enough, but actually it works with the stock 3K resistor, and it might be because I'm using it as a pull-up rather than on the load output, but anyway, it is working fine, and in terms of the signal we need to control, that's all fine. So what we've ended up with, I'll leave you with that. We've got our 1K just to drop the signal so we don't overload the the LED, make sure we don't burn that out. They do have a certain duty cycle, you know, so many tens of thousands of cycles, and how much current you put in, eventually it will burn out at some high level. So definitely want to keep that nice and under control. And on the other side we've got our 3K to make sure the frequency response is okay, and that seems to be working. So we're going to stick with that for now, unless we find an issue. And we've got a nice clean input to the ESP from the VFD, and it's completely isolated. It's galvanically separated, so that's a nice thing as well. And it replaces having to use an op amp to do this comparison as well, so it's kind of 2 in 1. And it replaces the voltage divider. We don't need to drop down from 10 volts to 5 volts using just a resistor network there. We automatically get that because of the pull-up. The only thing is it's inverted, but in the software I just look for a high meaning it's a low, and a low meaning it's high, so that's trivial to switch around. So that's what we're using, and I think we'll go forward with that. Okay, so basically made my own version of that. You probably can hardly see it, but just in there is my opto comparator. That's a PC817, and then I've got my positive signal coming in from the inverter. That's out of V0, and then that's my common return. So that's the signals coming in. I've got a couple of resistors, one to manage the current through the opto isolator, because obviously there's a little LED in there. And then I've got my little indicator LED. In fact, if I just spin the motor up. So the faster it goes, the brighter the LED, because it's being run from a PWM signal basically. And then on the other side I've got 5 volts across the transistor inside the opto coupler, and then I've got a little resistor here just to pull it down to 0. So it pulls it to 0, and then when the transistor triggers, it goes up to 5 volts. And I had to get just the right value of resistor so that I'd get a reliable 0 to 5 volt signal. But also you've got to watch the rise times in milliseconds, or microseconds actually, for the transistor, and make sure, you know, it's going to react pretty quickly. So that is now working really well. I've got nice strong pulses, nice and clean, and as a bonus I'm opto isolated from the inverter, at least through the signal side. Okay, then in terms of the spindle speed, I'm still using the IR sensor and it's putting out its signal when this reflective tape goes round on the spindle, but instead I'm now putting that, rather than through that little decoupling capacitor that wasn't super reliable, I'm now putting it through an op-amp which I'm using as a comparator. I do have some dedicated comparators, but I think this will be fast enough for what we're doing. And then I've got a 2.5 volts reference signal via that pot there, and all that's happening is, although the signal can be a bit noisy, as long as it's below 2.5 you get a low out, and as soon as it goes above 2.5 you get a nice high, so you get nice solid pulses out. And as soon as I did that, the speed count was 100% robust, no problem at all. So I've now got two strong, nice clean signals that I can see what's coming out, what's being demanded from the inverter, and then what's actually coming out the spindle, and that's made life a lot easier. Okay, you may be able to, just about be able to see there's the infrared sensor module there. That's already got a comparator on it, so I'm sending a reasonably clean signal out, but it does have a little bit of noise, into my comparator, which then making it super clean. So what I'm going to do actually ultimately, it looks like this. I'm going to replace it, and I'm not going to have this module in. I'll just have the infrared send and receive as their own little module. I've got a really tiny one, I'll show you that in a minute. And then I'll have my own comparator circuit on the board down here, and that'll allow me to do the adjustment via a potentiometer like this remotely, rather than having to try and work out how to do it in there. That'll make that whole head an awful lot smaller, and also because I'm using my values I can tune this just as I want, rather than getting stuck with the resistors and capacitors they've got on this module board. And even at this low speed you can already see the problem is the pulse is not very wide, and that's part of the reason I think why I was running out of RPM. So this time though we've got a little potentiometer. Make it a little bit better until it saturates. Okay, so let's try that. So I'll switch the VFD signal on as well, and then you can see down here they're very close. Let's ramp it up, see how high we can get it. Seven, 8, 9, 10, 12, 14, 16, 18, 19, 20. Max there. Looks like it needs a tiny bit of calibration, but it's okay. Okay, I think it's about time we made a new sensor head for the spindle, so I've just redesigned and 3D printed this little housing. I know it's a bit dark in there, but basically what's going to happen is I've made this little circuit here. It's not finished, but I've just cut it off that piece there. And then that'll have the little infrared send and receive LEDs on it, which will go onto there, and then they'll like stick out the back of this board, and they'll go down through those two holes there, and then they'll come out the other side, and then they will shine onto the part that spins around like that. So they'll just be down there picking up off that little white piece there. So that's the idea. And then once I've got those LEDs on the back, and I've got to put a few little components and resistors, then I'll put 3 little cables on there, 3 little wires. It was something. I'll cut this off. This was a bit of a test piece. They'll go into there, and then all of that will drop into there like that. And then if you can see, there's a little screw there which goes into that fitting, with the cables. There's a little bit of cable relief just there, and then made this little lid with a bit of a gap for the cable as well, and then that will go on there like that. So we should have a nice self-contained little unit. Now it's not going to be watertight. I'll have to see if I can get a little rubber gasket to go around there in the final design, but I think it'll be a big step forward, and it'll probably make this end a little bit more robust as well. So let me get that soldered up, get the components on, get it installed, and then we'll bring you back. Okay, it's mostly built now. I've got our infrared LED on there, and then a terminal block, a couple of resistors, one for the LED and one will be for the receiver. Now before that went in there, when they arrive the legs are the same length and there's no flat on the side that I can see, so it's hard to see what the polarity is. So before it went in there I just checked which way around. I got this on the diode setting on there, and if we put it what would be the wrong way, so we don't get anything at all, if we put it this way around we get our reading there, there we go, 1.1. Okay, so I know which way around that's got to be. The problem is you can't do that same trick on the photodiode, or not. Oh, look, where did that go? The legs are about the same length. There's no obvious flat that I can see. Maybe there is, but it's really small. So what I'm going to do is just power this up, put 5 volts through it. I'm just going to hook it up to the power supply, and then this will shine. Well, obviously we won't see it, and then we can just check across this as we bring it closer, and then determine which is the anode, which is the cathode. Now you've got to be a bit careful on these photodiodes. If them to work in the way we want, you end up putting them backwards in the circuit. So switch it on. Got 5 volts. I've got this in diode mode, and then we'll, as you can see on there, legs are about the same length. There's no obvious flat that I can see on there, so we'll just randomly pick a side and see if we get lucky. Do it around here so you can actually so you can see it. All right, and bring it close. Nope. Change it around. Okay, oh, don't want to go too close, get too much current through it, but yeah, okay. So that one on the left there, I'm going to bend it a bit. That is the cathode, that's the anode. So I did think about getting this little board made. I did draw it in EasyEDA with a few components and got the layout correct so it would fit in the housing. And then I thought, well, maybe I'd send away and get it made up. So this is a previous project. This was a solar monitor project. This is one of the prototypes, and I got them to make the board. This was JLC PCB. As you can see, made a really nice job of all the masking and all the tracks and everything, and then I added all the components, and then I iterated the design. As you can see, I still used it for further development. Yeah, but they make a really nice job of it. But in the end, it's just a one-off, so I'm just going to stick with a handmade sample, at least for now. Alright, so it's all finished there. I've just got temporarily wired into this little block, and before we put it in the housing, let's just check it's all going to work. Switch that on. Okay, then I'll just flash this in front and we'll see the RPM meter change there. Hopefully. Okay. Obviously that's not running because the spindle's actually not on. Alright, let's build this up into the housing and give it a test on the actual spindle. Just about to see the LEDs down there. Now I designed it so well, the screw head is well clear of the tracks. Or if it does get close, it's just going to run past the common track, so it won't do any harm. Yeah. And then brings up a little lid as well, but yeah. I won't put that on just while we're testing, but get the idea. Right, let's go and put this on the spindle. Okay, here we go. So we've got our spindle and then our VFD speed. Right, I've changed the code a bit, so we've now got spindle speed there and inverter speed demand there, and so it will monitor those, and if they drift too far apart it starts to increase this load meter down the bottom here. And we've also got our system state over there, so let's put some RPM on. So if this difference is quite small, we only get a couple of bars, so I'll just mess around with the acceleration and see how many bars we can get. So because there's a big difference in RPM, it thinks there's a load, so yeah, that's working okay. So I'm not quite sure what's going on. I've just had to change the microprocessor out for the third one. Basically it just stopped communicating with the port, so it wasn't recognised by the PC. You plug in the USB port and it wouldn't recognise it, so it couldn't connect, so it couldn't upload any code. So I plugged that one in, it's recognised that, and we're off again. I don't know, I'll have to look into that. Anyway, new update, so even more refinement to the code. It now does a running average of the RPMs, and you can independently tune how many averages it takes, because you've got different pulse rate coming in on each of those channels, so they're tuned independently, and now it's tracking really nicely, and it also detects the stalls a lot better. The other thing I've done is made some custom characters for the bars as they come up there. I'll show you that in the code, and yeah, it's working really well, so let's give that a demo. So now with the averaging, it doesn't jump around quite so much, and the value's pretty close. And then at the bottom you can see the custom characters, so that's a kind of load meter. So if I can change the RPM, and then got my glove on, we'll try and stall the spindle. I'll lower it down a bit to make it a bit easier. And there we go, it's detected that. Obviously we can tune that a little bit more, but that works really well. Okay, let's talk a little bit about Modbus. So in the last video I had some really great and helpful replies on that topic, so thank you very much for that. I didn't even think about going the Modbus route, mainly because on the original testing I tried to monitor the current and then loaded and stalled the motor, and it didn't really seem to track, so I assumed anything that was going to get broadcast on any kind of network was possibly also not going to track that load very well. I don't know for sure, but so I didn't even kind of think about that. But it does have Modbus control. I don't think I can read it. I think you've got to go kind of full control or nothing, which is a bit of a disadvantage for me, but I'll show you what we've got actually in the manual. Okay, so in terms of Modbus, you have to set the source of commands in this parameter here. So set by operator, I think it'd be front panel. Set by one, external terminals, which is what I've got. So on the front of my machine I've got stop start buttons and a potentiometer for speed control. It's not controlled by the software, because I can also use the machine as a manual mill as well, and it's quite nice to just stop start and change the speeds that way rather than do it in software. So that's the one I use. And then number 2, which looks like I didn't print the page out actually, but it basically just says 2 is Modbus, and then that controls everything. So if I wanted to go down that route, and again, thank you for the contributions, I didn't know this, there's a plugin for UC CNC which can read the Modbus and talk to it as well. So that would mean I'd have to add that in and then get the software to do the stop start and speed control. So as I've mentioned, that's less convenient for me. As far as I know in here, I can't just listen to the Modbus. and still have the external control. I don't think, it doesn't sound like I can have it that way around. So for now, I'm not going to dive into that. Maybe as a separate video, I'll set up another processor dedicated to see if I can get Modbus Red on an Arduino or an ESP32, and just have a look at what's broadcast, see if it would broadcast the current, and then install it and see if the current goes up, to see if that was even feasible. But for now, the system's working really well as it is, just direct. It's plenty quick enough for detecting e-stops, so I'm going to go with that for now. But it was a great suggestion, so thank you very much. Maybe it'll be a future video, but for now we'll carry on with the current strategy that we've got. Okay, that's it for this video. In terms of functionality, it's very similar to the end of the last video, but everything's been upgraded and I'm much happier with the performance of this. So we've swapped out the Arduino for the ESP32, so we've got a lot more processing power. In terms of the infrared sensor, I've made a custom sensor, I'm much happier with that. And then I've also got my own custom electronics, so I can dial that right in using that op-amp as a comparator there. For the inverter signal, we got that going through our optical isolator or optocoupler, and again I'm much happier with that because it separates the two systems, which is never a bad thing. And then the code is much more robust now. It's got running averages in it, and it's just tuned in a lot better. The algorithm for the e-stop is now much better, and I haven't had any false e-stops since I put that new code in. And then that kind of load meter, the visual load meter, is looking quite nice as well, to give you some idea of if you're getting near to the e-stop limit. Okay, so if you've enjoyed this video, feel free to subscribe if you want to see how this turns out, and feel free to leave a comment as well. That's always very helpful. It may guide the future direction of this project. And with that being said, thank you very much for watching, and see you next time.